Hi everyone. So welcome to lecture number 7 of the counting course that we are doing. It is a part of data science and AI course, complete GATE course on YouTube. So in this lecture we will solve a few problems on whatever we have discussed in the previous 6 lectures, like factorials, permutation, combination, with and without repetition. Okay, so I will try to take a generic example and try to explain like where to apply which thing, like combination with repetition, permutation with repetition, without repetition, combination, and so on. So we have discussed so many things, but like for what type of problem, what formula or like what logic do we apply, that we will see in this lecture. Okay. So firstly, a quick recap. So for combination with repetition, the number of combinations of n objects taken r at a time when repetition is allowed was n plus r minus n choose r. For permutation with repetition, like you have r places, n objects. It doesn't matter, like you have n options for every place, so you have n to the power r options. So just to summarize everything, if the order matters, see, like I told you, the difference between permutation and combination was what? In permutation, order matters, it is arrangement. In combination, order doesn't matter in which order we are picking, only the selection matters. So if order matters, it is permutation. If order doesn't matter, it is combination. And also the question might be like the repetition is allowed or not. So if order matters and repetition is not allowed, so basically you have n objects and you have r places. So you have n options for the first place. For the second, since repetition is not allowed, you will have n minus 1 options for the second place, and so on. You have n minus 2 options for the third place, and basically you will have n minus r minus 1 options for the last place. So the number of permutations was npr. We already saw it. Okay, npr. The number of ways in which we can arrange r objects out of n objects. Now, if the order doesn't matter and you cannot repeat objects, it is just like selecting r objects out of n objects. So here we were overcounting, so we divided it by r factorial because we were overcounting every combination r factorial times. So it became NCR, the number of ways in which we can choose r objects out of n objects with no repetition allowed. Now if permutation, if order is important, so you have to arrange, but repetition is allowed. So basically for every place, since repetition is allowed, you have n options here and n options here and n options here and so on. So it becomes n to the power r. Permutation with repetition. And if order doesn't matter, and repetition is allowed, so it is combination with repetition. That's the most complicated one. And here you have to map it to an equation x1 plus x2 up to xn equal to r. And the number of ways to solve that equation is n plus r minus 1 choose r, which is this. So this is the summary of what the formulas which we have seen so far. Okay. So now let's solve some problems. So always like when solving problems, pause the video. I will like step aside and you can pause the video and then you can try to solve it on your own, and then you just see the solution. Okay. So this is the first example. So in how many distinct non-negative integral solutions are there? Again, non-negative integral solutions. So basically x1, x2, x3 can be all greater than or equal to 0. So how many distinct non-negative integral solutions are there for the system of equations? This. So anyways, they are non-negative integral solutions because x1 is greater than or equal to 2, x2 is greater than or equal to 3, x3 is greater than or equal to 1. So it's a standard problem. We already saw how to solve it. So see, if x1, x2, x3 had been greater than or equal to 0, the problem would have been simpler, right? We already know it. If x1, x2, so if the problem was this, x1 plus x2 plus x3 is equal to 12, and x1, x2, x3 greater than or equal to 0. If the problem had been this, we already know how to solve it. Just create 12 plus, since we want 3 partitions, so we will insert 2 sticks. So 12 plus 2 is n plus r minus 1 is 14. In 14 boxes, you insert 2 sticks and you will get a different solution every time. N plus r minus 1, choose n minus 1. So 14 see 2 ways in which we can solve this problem. But here we have a constraint. x1 has to be greater than or equal to 2, x2 has to be greater than or equal to 3, and x3 has to be greater than or equal to 1. So what we will do, we will try to map this problem in some another space which we find easier. Since x1 has to be greater than or equal to 2, see here we will have a solution like this also, 0 plus 0 plus 12. But this is not allowed. Since x1 has to be greater than or equal to 2 and x2 has to be greater than or equal to 3, this is not allowed. This has to be at least 2, this has to be at least 3. This is allowed. Okay. 2 plus 3 plus whatever, 7. Right? But this is not allowed. So we will map it to some other space. So basically we will give at least 2 to x1. We will give at least 3 to x2. We will give at least 1 to x3. So basically we will write x1 as 2 plus a. And we will write x2 as, since x2 has to be greater than or equal to 3, we will write x2 as 3 plus b. And since x3 is greater than or equal to 1, we will write x3 as 1 plus c is equal to 12. Okay, we are writing x1 as 1 plus 2 plus a, x2 as 3 plus b, and x3 as 1 plus c. So this way the equation becomes this, and since x1 is greater than or equal to 2, and I am writing x1 as 1 plus a, 2 plus a, so this equation becomes this. So basically now the equation becomes a is greater than or equal to 0. That's what I wanted. Similarly for x2 also, I am writing it as 3 plus b, so it will become b is greater than or equal to 0 and c is greater than or equal to 0. So now this equation becomes this with a, b and c greater than or equal to 0. So this equation is nothing but a plus b plus c a plus b plus c is equal to what? 3 plus 2, 5 plus 1, 6. A plus b plus c is equal to 6 where a, b and c greater than or equal to 0. You already know how to solve it. 6 plus 2, 8 C2 solutions. N plus r minus 1 choose n minus 1. So 8 C2 solutions are there to this equation, which is 8 into 7 by 2, 28. Okay, there are 28 solutions to this equation. Okay, now a different question with more complications. So now we will try to solve this. So just pause the video and try to solve it on your own. Cool. So this is the system of equations that we want to solve. Okay, x1 plus x2 plus x3 is equal to 12. x1 has to be between 2 and 10 inclusive. x2 and x3 can be anything between 0 and 12. So there are no restrictions on x2 and x3. Basically they can be anything between 0 and 12. So there is basically an infinite supply of x2 and x3, you can assume, right? Because anyways we will never have x2 as 15, like that won't satisfy, right? So x2 and x3 we have infinite supply, we have 12 of them. There is a restriction on x1 unknown. It has to be between 2 and 10. So this side wala inequality we already know how to solve. If x1 has to be greater than or equal to 2, that we already know. How to solve that? Just give at least 2 to x1. So write x1 as 2 plus a. So at least, so we will do that first and then we will see how to solve the problem, okay? So, okay, firstly, like very basic thing, how to solve this problem, x1 plus x2 plus x3 is equal to 12, where x1, x2, x3 are all greater than or equal to 0. If only this was the restriction, we know that there are 14 C2 solutions. Okay, we will apply the formula 12 plus 2 C2, okay? Now, forget about this, we have a new restriction, and that restriction is that, okay, I am not taking x2 and x3 in the picture because x2, x3 have no restrictions, okay? So now the question is, x1 has to be between 2 and 10, okay? For now, let's, okay, so how to solve this side of the formula, this side of the equation? Since x1 has to be greater than or equal to 2, I will write x1 as 2 plus a, so that x1 is now greater than or equal to 0. So now I will write x1 as 2 plus a. So this will become 2 plus a plus x2 plus x3 is equal to 12. 2 plus a. So now this equation will become what? Since x1 is 2 plus a, I will write it this way. 2 is less than or equal to 2 plus a is less than or equal to 10. Subtract 2 everywhere, it will become 0 is less than or equal to 8 is less than or equal to 8. Right? I have written x1 as 2 plus a. So x1 has to lie between 2 and 10. So now a has to lie between 0 and 8. Right? So now this equation is what? A plus x2 plus x3 is equal to 10. We don't have restrictions on x2 and x3. Basically, x2 and x3 are between they are still between 0 and 12. So they have to be just greater than or equal to 0 and less than or equal to 12. Less than or equal to 12 will always satisfy, right? Because the equation is only up to 10. So this will anyway satisfy. But the more difficult problem is A has to be between 0 and 8. So this side of problem is now okay. A has to be greater than or equal to 0. So if the problem had been only this, if this restriction had not been there, then the number of solutions would have been 12C2. If we remove this restriction, A has to be less than or equal to 8, then A x2 x3 can be anything greater than or equal to 0. Then the number of solutions to this system of equations would be what? 12C2, n plus r minus 1, choose n minus 1. But among these 12C2 solutions, I told you, the more generic way to solve this problem is using inclusion and exclusion, right? But here we don't need inclusion exclusion. Here we are just overcounting a few solutions. What are we overcounting? See, A has to be less than or equal to 8, which means that the only values which are not allowed in A are what? A cannot be equal to 9 and A cannot be equal to 10. Right? If we are solving this equation without this condition, we will have a few solutions, like we will have A equal to 9, x2 equal to 1 and x3 equal to 0. We will have one solution as A is equal to 9, x2 is equal to 0 and x3 is equal to 1. And we will have one solution A is equal to 10, x2 and x3 are 0. These three solutions are not allowed. I hope you got it right. These three solutions are not allowed because A is less than or equal to 8, A cannot be equal to 9 or 10. These are the only three solutions in which A is exceeding 8. Right? So basically these are the three solutions which we are overcounting. So we have to reduce them. So there were 12C2 total solutions to this equation. 12C2 minus 3 is our answer. We have three solutions we are overcounting. So what it will become? 12 into 11 by 2 minus 3, which is 66 minus 3, 63. So there are 63 different solutions to this equation, system of equations, okay? So always like it will be a simpler problem, solve this side of equation first and then this equation will reduce and you have to subtract what you are overcounting. Okay? So now let's move to the next problem. Your mother-in-law buys 1,000 small gifts. Buys 1,000 small gifts to give to relatives for Christmas. 1,000 gifts. Each of the 1,000 items are different. 1,000 different small items. Okay, I1, I2, up to I1000. There are 1,000 different items. There are 25 relatives to give these gifts to. There are 25 relatives. How many ways are there to distribute the gifts? Okay, so nothing is mentioned. So basically any relative can get any number of items and all the items are different. And since nothing is mentioned, you cannot repeat these items, right? By default, like if you read this problem statement, it is very clear that you cannot repeat the items. If you have given some gift to someone, you cannot give one gift to two people basically. There are exactly 1,000 different items, gifts, and you have to distribute to 25 people. That's all. So how will you do that? So basically for like just create buckets. Let's say this is first relative. This is second relative. This is third relative. And this is 25th relative. And let's say I'll name gifts better. Let's say I have 1,000 gifts, right? So I'll write it here. Let's say this is the first gift, G1, G2, G3, and so on. I have 1,000 gifts. So how to solve it? Any relative can get any number of gifts. So solve it this way, okay? Rule of product. For the first gift, so basically solve it using the rule of product. Distribute gift first for the first gift, and then distribute the second gift, and then distribute the third gift, and so on, and then distribute the 1,000th gift. So and okay, multiply. So in how many ways can I distribute the first gift? I have 25 relatives. I can give the first gift to anyone. I have 25 options for the first gift. I can give it to any relative. And I have 25 options for the second gift. I have 25 options for the third gift. And so on. I have 25 options for the 1,000th gift. So basically I have 25 different options for any gift. So this is how I'm writing it. Let's say this is the first gift, second gift, and the 1,000th gift. So basically, let's say I'm giving this gift to relative, third relative. This I'm giving it to 17th relative, and so on. Like this, I'm giving it to the first relative. So this is one possible option way to do that. Or I can give all the gifts to the first relative only. That is also an option. Okay, and so on. So basically, I have 25 options for all the gift items. So the number of ways will become 25 to the power 1000. 25 into 25 into 25,000 times 25 to the power 1000. Okay, this is the number of ways in which I can distribute these gifts. Now let's see another variation of the problem. So again, your mother-in-law buys 1000 small gifts to give to relatives for Christmas. Each of the 1000 gifts are again different. Again, there are 25 relatives to give these gifts to. But now, how many ways can these gifts be distributed so that each person gets 40 items? Now, previously there was no restriction on any gift. One gift can go to anyone. But now there is a restriction for every gift. Every person should get exactly 40 items. See, there are 25 relatives, and if everyone gets 40 items, it is 1000. Basically, you are distributing every gift. But you are not doing partiality. You have 1000 different gifts, but you will give 40 gifts to everyone, every of the 25 relatives. So in how many ways can this distribution be done? So think of it now. So let's say this is the first item, this is the second gift, this is the third gift, and this is the 1000 gift. Okay, and this is the gift box. Like it contains all the 1000 gifts. Okay. And for every relative, let's say this is my first relative, this is my second relative, and this is my 25th relative. Now what happens here? See, it doesn't matter. Let's say the first relative is getting the first 25 gifts. The first 25 gifts. The second relative is getting the first 40 gifts. Okay, every relative is getting 40 gifts, right? Okay, so every relative is getting 40 gifts. So let's say this is my first relative, this is my second relative. So let's say the first relative is getting the first 40 gifts, and the second relative is getting the next 40 gifts, and so on. This is one possible option, right? But the order doesn't matter, right? The relative 1 doesn't care if the first relative is getting 1, 2, 3 up to 40 or 2, 1, 3 up to 40. The order doesn't matter. You just have to pick any 40 items out of this 1000 items and give it to first relative. Then from the remaining items, you take 40 items and give it to the second relative, and so on. So if you have to break this problem down using the rule of product, how will you do it? So let's say you have 1000 gifts to give to. So let's say this is your first task T1. It is distribute. Not distribute. So I should write it this way. So this is the first task. Give 40 items. Give any 40 items. Give 40 items to the first relative. This is my first task. And then my second task will be to give 40 items to the second relative. Right? Because I have to distribute exactly 40 items to R2. Right? But here, when I am distributing to first relative, I have 1000 items. So out of 1000 items, I have to select 40 and give it to R1. Here, when I have already given 40 items, I am left with only 960 items. So from the remaining 960 items, I have to take 40 items and give it to R2. So from the remaining 960, this is my task T2. And the third task will be, now give 40 items to R3, the third relative, but now you are left with only 920 items. Since you have already consumed 80 items, 40 here and 40 here. So from the remaining 920, you give 40 to R3, and so on. For the last relative, the 25th relative, you will be left with 40 items only. So you have to give the remaining 40 items to this relative. Okay, there is only one way to do that. Just give the last 40 gifts to the 25th relative. So in this way, I am counting all possible options. Okay, and this problem can be solved using a very beautiful equation as well, which is called the multinomial equation or the multinomial theorem. We will see it in the next lecture. But there is another way to see this problem. Okay, by creating a multinomial equation. But I hope you are getting it. Okay, the formula here. So what we are doing here basically, from the first 1000 items, so what is the number of ways to do the first task? Choose any 25 items and give it to the first relative. This is my T1. And then from the remaining 960 items, choose 25 items and give it to the second relative. And then from the, sorry, not 25, we are selecting 40. Okay, so from 1000 we select 40. Then from the remaining 960 we select 40. Then from the remaining 920 we select 40. And so on, all the way up to the 25th relative where we have 40 items and we select 40 and give it to that guy. Okay. So now how to solve this equation? You can expand it. So this 1000 C40 will become 1000 factorial upon 40 factorial times 960 factorial. N factorial upon R factorial, N minus R factorial. Similarly, the second one will become 960 factorial upon R factorial, N minus R factorial. 960 factorial upon 40 factorial, 920 factorial. Similarly, this will become 920 factorial upon 40 factorial, and 920 minus 40 is what? 880 factorial. And so on. The last one will become 40 factorial upon 40 factorial times 0 factorial. Okay, N minus R is 0. 0 factorial is 1, right? So what will this become? This will get cancelled, this will get cancelled, this will get cancelled, and so on. So this, all the numerators will get cancelled, and in the denominator we will have, so in the numerator we will only be left with 1000 factorial. And in the denominator, in each of these factors we will only have 140 factorial left. We will have 140 factorial left. How many times? So there are 25 relatives, so 25 times. So in the denominator we will have 40 factorial to the power 25. Okay. So this is your number of ways to do this. This is slightly complicated problem. This might not be asked in GATE, but a simpler version of it might. Okay. So even if you don't understand it completely, it's okay. Okay. This is like involving everything. And also by seeing the next lecture, binomial and multinomial theorem, this problem will become much more clearer. Okay. It will become easier. We have not seen this type of problem before, like in PNC. So yeah, but yeah, this problem was easier. Okay, this you might have got. Like here it was much more simpler. Here because there were no restrictions. How many gifts are going to which guy? Cool. Now let's see the next variation of the same problem. So now the next year, what happened? Your mother-in-law buys 1000 identical pens to give to the family. Okay, now we don't have 1000 different items. Now we have 1000 identical items. We have 1000 identical items to give to the family, and they are giving pen. So now you start to wonder what is going on. Okay. So how many ways now these 1000 identical pens be distributed to the 25 family members? Okay. Now see, amazingly this problem became combination of repetition. You have 1000 identical pens. It doesn't matter. Okay, the items are not distinct; they are identical. So first pen is same as second pen, and so on. And you have 25 relatives to give it to. First relative, second relative, and 25th relative. Since the pens are identical, the relatives don't care which pen they are getting. They only care about the count, how many they are getting. Right? You have 25 relatives. So the first relative doesn't care which pen among those 1000 pens he is getting, right? They only care how many pens they are getting. So the number of ways will be what? You can either give all the 1000 pens to the first relative, or you can give like some weird combination, like you can give 40 to each one of them. That is also a possible option. Or you can give all 1000 to like 17th relative and so on. So it is just like, let's say the first relative gets x1 pens, second relative gets x2, and so on. The 25th relative gets x 25 pence, and you have to distribute total 1000 pence. So how many solutions are there to this equation? Where x1, x2 up to x25 can be greater than or equal to 0, right? Any number of pence can be going to any relative. So just the number of different solutions to this equation will be the number of ways in which you can distribute. So this will be equal to how, what? N plus r minus 1. So this is n, this is r. So n plus r minus 1, choose n minus 1. So basically you create 1024 boxes. Since you need 25 partitions, you will need 1024 boxes and you will create 24 sticks. So you will have 25 partitions and you will be remaining with 1000 boxes. We already saw this, apply the formula, okay? So this is the number of ways in which you can distribute 1000 identical pens to 25 different relatives. Cool. Now the last variation of this problem. Again the next year your mother-in-law buys 1000 identical pens and you have to distribute it to 25 relatives, you can assume. But now, in how many ways can I distribute 1000 identical pens to 25 relatives such that each person gets 40 pens? Now it is given that you have to distribute exactly 40 pens to every relative. So it is like you had 1000 pens and you have 25 relatives. See, the pens are identical, they look exactly same. You have to give 40 here, 40 here, 40 here, exactly 40 here. It doesn't matter which pen you are giving to which relative, they are identical. And they are saying you have to give 40 to each one of them. So you don't have any option, you just have to take 40 and give to R1, 40 and give it to R2 and 40 and give it to R25. You are left with no pens, right? So since the pens are identical and the count is also given, you don't have any option. Okay, this is the only way in which this problem can be solved. There is only one way in which this distribution can be done. There is only one way in which this distribution can be done, and this is the way. Give 40 pens to R1, 40 to R2, and so on, give 40 pens to R25. So this is the only distribution possible, so there is only one way to solve this problem. Since the pens were identical and the count was also given. In the previous problem, we actually counted in how many ways this bifurcation can be done. But here this bifurcation is also given. You have to do it 40 plus 40 plus 40 up to 40 up to 25. So there is only one way in which you can solve this problem. Just distribute it. Okay. Cool. So these were a few problems on permutation and combinations, and basically like with repetition, without repetition, whatever we have seen. So in the next lecture, we will continue the journey of counting. So see you tomorrow. Bye bye.